Good morning, everyone. We are doing Chapter 7, Rotational Kinematics. So for this chapter, we are covering rotational quantities, relationship between linear and rotational quantities, uniformly accelerated rotational motion. So these are the three subtopics, right? How do I move this? Okay. After completing this chapter, you must be able to define angular quantities, relate between angular with linear, and solve problems on kinematics of rotational motion. Alright, so these are the learning outcomes, which means that these are the things that you will be asked on the exam. Okay, so chapter 7 is on your final. Your test covers from chapter 3 up to chapter 6. So chapter 7 and onwards is your finals. Okay, so introduction, rigid bodies, object of definite shape, no physical change while in motion. For example, I have a ball. And it is rotating and also moving forward. So the ball, even though it is rotating and also moving, it does not change its shape. The ball remains the same, right? So this is called a rigid body. Rigid bodies are made up of particles. The motion of a rigid body can be translational, which means that it's moving to the right, it's moving to the left, it's moving upwards, it's moving downwards, moves at an angle. Anywhere, it's called translational. However, if it is moving at around its center, it is rotational. That is called a rotational motion. And then we have the combination, which is translational and rotation, which is the example that I given you just now, which is this ball is rotating. It is also moving forward. When you roll a ball, you are not just rotating it, it is also moving forward. So that is called the combination between translational and rotational. So translational is just moving it normally. Rotational is making it move about at its center. Combination is making it move about at its center like a ball, but also moving forward. So that's the combination of both. Alright, so translational motion of rigid bodies. In translational motion, all particles will have the same displacement. So for example, I have this object and the displacement of the white dot, the displacement of the red dot, and the displacement of the yellow dot is the same. For example, if the red dot is moved by 10 meters, the white dot also moves by 10 meters and the yellow dot also moves by 10 meters. Translational brings all the particles at the same displacement no matter where they are. So if I'm talking about a black dot over here, and at this point the black dot should be around here because the black dot will only travel about 10 meters. Okay, so if it starts from further back, it will end at further back as well because the displacement is constant. Okay. In rotational motion, you need to specify the axis of rotation. For our ball, our axis of rotation was the center of the ball. For this triangle, is the center of the triangle. Each particle moves in a circular path. So let's say I have a particle, the ball is made up of particles, and I have a particle over here. My angle of rotation starts at the center. If I'm talking about a particle over here, my center of my axis of rotation is here. My particle over here, my axis of rotation is there. Okay, so all objects has axis of rotation. Okay, axis of rotation. This is axis of rotation. Okay. So draw. Alright, so eraser. Oopsie. Control Z. Just want to get rid of that. So particle, 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 particle. So axis of rotation is here, axis of rotation is here, axis of rotation is here. Now, when my particle, let's say this is particle A and this is particle B, this is particle D. Let's say particle A moves by 10 degrees, right? So the ball moves by 10 degrees, which means that particle A also moves by 10 degrees. So particle A ends up here. Particle B also moves by 10 degrees and it ends up here. Particle D also moves by 10 degrees and it ends up here. Okay, so they rotate the same angular displacement but of different radius. What does that mean? So here your radius was the radius of the ball. Let's say it's 5, but the radius of this particle is 3. Maybe, I don't know. The radius of this guy is 2 meters. We don't know, right? So they have the same angular displacement. Angular displacement is the angle that they rotate, but different radius. So the radius is dependent on where the particle is situated with respect to its axis of rotation. In rotational motion, each particle moves in a circular path. We know this, with the same angular displacement, but of different radius. We know this. But what is angular displacement? Okay, I hope the next slide explains this. So it doesn't. Okay, nanti kita explain. The polar coordinate system. Okay, so kita punya regular coordinate system is x and y's and z's, right? So we have axis z, we have axis y, we have axis x. So let's say I have a particle situated over here. I can label this as x1, y1, z1. Okay, I know this. This is the Cartesian coordinate. It's called Cartesian coordinate. For the polar coordinate, we describe the position of our particle or the object by radius and by angle. Okay, so radius from the center and the angle from maybe the origin from here. So this is 2 and this is theta 1. This is radius 2 and this is radius 1. Radius, this is also radius 2. Okay, so you describe a particle by its radius and also its angle. That is the polar coordinate. Okay, so when a particle moves in the linear displacement, you will say that the particle moved from coordinate x1, y1 to coordinate x2, y2, right? So your final your change in displacement will be, sorry, it's S. The change in displacement will be x2 minus x1, and the change in the y is y2 minus y1. So that's your displacement, and that is linear displacement. But for angular displacement, the change is in radius and the change is in theta. So it's r2 minus r1 equals to theta 2 minus theta 1. And since the radius is the same, so there is no change in the radius, so the only change here that we are seeing is theta. So change in theta is actually called angular displacement. Okay, again, this guy is called linear displacement and this is called angular displacement when there is a change in theta. There is a change in theta, but the radius is the same. Okay, so that is angular displacement. So angular displacement is change in theta, whereby theta final minus theta initial. The angle swept by the radius in the time interval. Okay, so this is your reference point, 0, and this is theta 1. Let's say it's 20 degrees or 20 or 0.1 radian. You can say in radian or in degrees, and your theta final is, let's say, 40 degrees. So your change in theta is 40 minus 20 because theta final minus theta initial. Alright? So the angle swept by the radius in time interval, the unit is in radians. So if you are given with degrees, you should convert it to radians, and if you have it in radians, then that is the correct unit to have. Okay, so if you have an arc length, which is S, this is called arc length. Okay, kalau the whole circle is called circumference, so this is called arc length. Arc length is given by S, and your R is your radius. How do you find the theta? So this is the equation. Theta equals to S over R, or S equals to R theta. Remember, we also had an equation that looks similarly to this, which is V equals to R omega. But this one converts linear velocity to angular velocity, which is omega. Yeah, this guy is arc length to theta. Okay, so you need to know the radius of your circular motion. Okay, so one complete circle is 360 degrees. This is common knowledge, which is equal to 2 pi radian, which means that 1 radian is just 360 degrees divided by 2 pi, right? I just transferred this value over here. 360 divided by 2 pi gives me 1 radian. Okay, just now we talked about angular displacement. Now we are talking about angular velocity. Of course, when we have displacement, we also have velocity, because time keeps on moving. And when we have angular velocity, we will also have angular acceleration. Okay, so don't be surprised. Okay, so what was angular displacement? Angular displacement was delta theta, right? Which is theta final minus theta initial. And this is for angular, and this was for the linear one. We have delta x or delta s for displacement, final minus initial. Okay, and then we have for angular velocity, the equation is given by the rate of change of theta, and this means average. So average velocity, average angular velocity is it's omega, whereby delta theta over delta t. In the linear world, we have v, average, equals to delta s over delta t, right? Okay, so it's similar, but not really. It's for circular motion, and this is for linear motion. The unit is radians. Remember, your delta theta is in radians. That was the SI unit. If it is in degrees, you need to convert it to radians. And your delta t is obviously in seconds. So your average angular velocity is radians per second. This is your unit. Okay? And then we have instantaneous angular velocity, which is when your time approaches 0, the limit of time approaches to 0. And this becomes delta theta over delta t becomes d theta over dt. Okay, the time is super small. We talked about this for the linear velocity. And this just means the instantaneous angular velocity, which means that the speed at that particular point. So if I know my average speed, I want to know what is the speed at this particular point. So that is, I'm asking for instantaneous angular velocity. Yeah, it's the same concept, except that it's in circular motion. Okay, so in rotational motion, the circular motion of each particle repeats itself right along the circular path. So I have a particle and I am repeating this motion over a circular path. Thus, the angular velocity is often expressed as the angular frequency of the motion. Now, frequency, we learned about this before in chapter 6. We have period, that is t, and then this period is in seconds, that's the SI unit. And then we have frequency, which is 1 over period or 1 over t. And the SI unit is over second or hertz. We have angular velocity, which describes 2 pi over t, which is 1 complete cycle over 1 period. That is why it's 2 pi over t. How long does it take to complete 1 cycle? That is omega. Okay, and this is in radians per second. Then we also have angular frequency. It's just the same thing, except that f equals to 1 over t. And I'm just substituting f in place of t. If 2 pi over t, I substitute f into my 1 over t. That just means 1 over f, right? So 2 pi over 1 over f gives me 2 pi f. So omega is 2 pi over t or 2 pi f.